Welcome back to QHSE Talks. So I want you to imagine for a second that you take a massive puddle of a highly volatile solvent.
Okay, a big puddle.
Right, and you lock it inside a perfectly sealed, spark-proof, completely fire-rated concrete vault.
Sounds pretty secure.
You would think so, right?
Yeah.
You close this heavy steel door, and you might think, well, I've just completely contained the danger here. I've done everything right.
Yeah, that's the natural assumption. You locked it away.
Exactly.
Yeah.
But in reality, by sealing that room perfectly, you haven't contained a hazard at all. You have literally just built a pressure cooker bomb that is, just waiting for a single trigger.
It is a terrifying scenario when you look at the physics of it.
It really is. And we are speaking directly to you today, sitting right here at the table with us, because whether you are managing a sprawling industrial complex, or maybe you're an aspiring safety professional currently cramming for your upcoming ASP exam, this applies to you.
Absolutely. You need to master this stuff.
Right. So this session of QHSE Talks is all about looking past those really obvious hazards and understanding the invisible mechanics of the workplace.
It's a great space to be in today because that scenario you just described, it perfectly highlights the fundamental tension we deal with in hazardous materials management.
The tension between the chemical and the environment.
Right. I mean, we are dealing with incredible amounts of potential energy that inherently just wants to release itself into the environment. So our entire goal today is to pull apart the actual mechanics of segregation and separation.
The real nuts and bolts of it.
Yeah, we're talking about flammable materials storage, the fluid dynamics of ventilation, and the physics of chemical incompatibility.
And to really get into those mechanics, we're looking at some of the most foundational texts in the entire safety industry today.
The heavy hitters.
Oh yeah, a big stack of them. We're drawing from OSHA's Process Safety Management Standard, that's 1910.119. We have the Center for Chemical Process Safety Guidelines for Risk-Based Process Safety right here on the table.
Excellent source.
We are also integrating the Handbook of OSHA Construction Safety alongside various CSP and ASP study guides. So the mission of this particular QHSE Talks is to completely decode ASP 11 Domain 4 Topic 9.
And we really need to emphasize, we aren't just here to memorize a list of numbers for a test.
No, definitely not.
Right, because that doesn't save lives. We are here to understand the why behind those numbers, which honestly is the only way to actually retain the information and apply it in the real world.
Because if you just try to memorize that, chemical A needs to be 20 feet away from chemical B,
yeah,
it's just a meaningless abstraction, it's just trivia.
Exactly. But when you understand the physical properties, like how a liquid actually spreads across concrete or how a dense vapor creeps along a floor well, those regulations suddenly become vivid blueprints for survival.
They become visible.
Right. This is about preventing catastrophic releases.
Mm-hmm.
It's about understanding that as a safety professional, you are essentially an architect. You build invisible walls and unseen currents of air to keep highly dangerous variables from colliding.
I love that. Invisible walls and unseen currents. Let's pull the thread on that idea of variables colliding. Because before we can even talk about how to construct a storage room, we have to look at the materials themselves.
Down to the molecular level.
Right. Let's start with the concept of incompatible materials. We throw that term around a lot in the industry, incompatible. But what does it actually mean when two chemicals are defined that way by the regulations?
Well, it basically means we are looking at materials that undergo a spontaneous and violent chemical reaction when they come into physical contact with each other.
So they touch and things immediately go wrong.
Very wrong.
Mm-hmm.
The standard definition tells us these are substances that can generate intense heat, toxic fumes, dangerous gases, or even explosive byproducts.
Wow.
Yeah. And let's look at the chemistry of what is actually happening there. When you bring two highly reactive, incompatible materials together, you're basically creating an environment where electron exchange happens at an uncontrolled, runaway pace.
So it is not just about a fire starting in a warehouse. We are talking about two relatively stable materials suddenly touching and transforming into a completely new, infinitely more dangerous environment.
That is the core of it. Take the classic example of mixing a strong acid with a strong base.
Okay, acids and bases.
Right. People often think of acids and bases as opposites that just, cancel each other out in a neutralization reaction. And I mean, while they do technically neutralize, the byproduct of that specific reaction is water, salt, and an enormous amount of thermal energy.
A lot of heat.
A massive exothermic reaction. So if you spill a strong acid onto a strong base in a highly concentrated form, the heat generated can be so instantaneous and so intense that the water being formed instantly flashes into steam.
Oh, wow. So it just explodes into steam.
Exactly. That steam expands violently, which causes the entire caustic mixture to just boil and splatter outward. It creates a geyser of boiling chemical burns.
That is horrifying. So the hazard isn't even just the chemical burn itself anymore. It is the thermal energy weaponizing the liquid, literally throwing it across the room at people.
Right. It's a kinetic hazard at that point.
You know, I was looking through the source materials, and there was another example that really caught my eye because of how insidious it seemed. It mentioned that if waste containing sulfide gets mixed with an acid, the result can be explosive.
Oh, yeah. That is a brilliant example of a secondary atmospheric hazard. When an acid comes into contact with a sulfide compound, you initiate a reaction that rapidly produces hydrogen sulfide gas, H2S.
Rotten egg smell, right?
Initially, yes. But here is the terrifying physical mechanism of H2S. At low concentrations, you smell the sulfur. But as the concentration rapidly builds from that chemical reaction, the gas literally attacks your olfactory nerves.
Wait, it attacks your nose.
Yeah, it paralyzes your sense of smell. You think the hazard has passed because the smell just goes away. But in reality, the concentration in the room is reaching a lethal threshold.
So your body's warning system gets shut off by the gas itself.
Exactly. And beyond the extreme toxicity, H2S is highly flammable. Its lower explosive limit is quite broad, so by simply letting a puddle of acid reach a pallet of sulfide waste, you have just flooded the storage area with a paralyzing, toxic, invisible gas.
And then what?
And then it just waits. It will detonate the exact moment a forklift drives by and creates a single spark.
Man, that makes me think of seating arrangements at a highly contentious family dinner.
Oh, that's a good analogy.
Right, you have two relatives who just absolutely despise each other. If you sit them at the same table, you are practically guaranteed a shouting match that ruins the entire event.
You have to keep them separated.
Exactly. The host of the dinner party has to physically map out the room to ensure they never cross paths. So in a warehouse setting, the safety professional is that host. We have all these troublemaking chemicals.
Lots of troublemakers.
So how much physical space do the fire codes actually require us to put between them to prevent these runaway exothermic reactions or toxic gas clouds?
Well, the fire codes give us very rigid pathways here. They break it down into a choice between segregation and isolation.
Segregation and isolation. Those sound like synonyms.
They do in everyday language, but in safety engineering, they represent two completely different physical strategies.
Okay, let's tackle segregation first. What is the actual physical mechanism of segregation?
Segregation is defined strictly by physical distance, nothing else. The absolute baseline rule you need to know is that incompatible materials must be separated by a distance of not less than 20 feet.
20 feet. I mean, that is the length of a large pickup truck.
It is a significant amount of space.
Right. And in a modern warehouse or a manufacturing floor, every square foot of real estate is calculated down to the penny for profitability. 20 feet of empty air between pallets is a massive operational footprint to just give up. Why that specific distance? I mean, why not 10 feet?
It comes down to human reaction time combined with the fluid dynamics of a spill. Let's say a 55-gallon drum of a strong acid gets punctured by a forklift tine.
Okay, a puncture.
That liquid doesn't just sit there politely. It spreads radially across the concrete. And concrete is porous, it has imperfections, it has slopes for drainage. The liquid is going to travel, and quickly.
So it's moving across the floor.
Right. So the 20-foot buffer is engineered based on the average spread rate of industrial liquids before they thin out enough to be manageable. And that's combined with the time it takes for a worker to realize a spill has even occurred, hit the emergency stop, and deploy a spill kit or a containment boom.
Okay, so the 20 feet isn't just empty space. It is a temporal buffer. It is literally buying you seconds and minutes.
Exactly. It ensures that the spreading acid puddle loses its momentum and its volume before it can physically bridge the gap and reach the alkaline material sitting on the other side of the bay.
That makes total sense.
And it also accounts for vapor dispersion. Many of these chemicals are fuming. As they sit there, they off-gas.
Even if they aren't spilled.
Right? Even just from small leaks or normal venting. If you only have 5 feet of separation, the ambient air currents in a warehouse could easily push a dense reactive vapor cloud from one pallet directly into the incompatible vapors of the neighboring pallet.
So the fire could start in the air itself.
Yes, initiating a reaction in the air. 20 feet allows the ambient air volume in the facility to dilute those fuming vapors below their reactive thresholds before they ever actually meet.
Okay, but let's play out the operational reality here. Let's say I am managing a site in a very dense urban area. I simply do not have 20 feet of empty floor space to give up. The business would have to shut down if we spaced everything out that far.
That is a very common reality.
Right. So what is the alternative strategy?
When distance is a luxury you do not have, you have to transition from segregation to isolation.
Isolation.
Isolation relies on a physical barrier.
Yeah.
Specifically, you can use a non-combustible partition to separate the incompatible.
Okay, so just put up a wall.
Well, the code does not allow you to just put up a standard cubicle wall or a flimsy piece of sheet metal between the drums. The geometry of this partition is heavily, heavily regulated.
Okay, what are the specific dimensions?
For you candidates prepping for the exam, this is a critical detail to write down. The non-combustible partition must extend not less than 18 inches above and 18 inches to the sides of the stored materials.
18 inches above the highest drum and 18 inches past the widest edge of the pallet. So it has to completely eclipse the footprint of the materials.
Completely.
That seems almost overly cautious to me. I mean, if the partition is non-combustible and it separates the two materials, why does it need to overshoot the pile by 1.5 feet in 3 different directions?
We have to go back to the physics of how a container actually fails, because containers rarely just quietly leak from a tiny pinhole.
Usually it's an impact.
Exactly. In a chaotic industrial environment, a drum gets dropped from a hoist, or it gets crushed by another pallet. When a sealed steel drum is subjected to sudden massive mechanical pressure, the liquid inside is incompressible.
Right, the liquid can't shrink.
No, so the energy has to go somewhere. The drum ruptures violently.
The liquid is subjected to sudden hydraulic pressure.
Right, and it sprays. It creates a highly pressurized arc of chemical fluid. If you have a partition that is exactly the same height as the drum, a pressurized rupture will send that liquid splashing in a parabolic arc right over the top of the wall.
Oh, just sailing right over the barrier.
Exactly, landing directly on the incompatible materials on the other side. So the extra 18 inches of height acts as a physical backstop. It's there to catch that pressurized arc.
Wow, so it is literally a splash guard.
Yeah.
And the 18 inches on the sides serve the exact same purpose.
Splash guarding plus vapor mitigation. Remember, vapors are fluids too, and they move kind of like water. If a drum leaks and produces heavy vapors, those vapors will pool on the floor and spread outward.
Seeking the lowest point.
Yes. And when they hit a wall, they don't just stop and give up. They creep along the baseboard looking for a way around. If the wall ends exactly where the pallet ends, the vapor just curls right around the corner and meets the incompatible vapor on the other side.
Just wrapping right around the edge.
Right. Extending the wall 18 inches forces the vapor to travel much further out into the open aisleway. This increases its exposure to the ambient room ventilation, diluting it before it can wrap around the barrier.
So the architectural requirements are actively fighting the physical behavior of the chemicals. That is fascinating.
It's all about physical countermeasures.
Okay, but what if we are dealing with smaller volumes? Say we don't have entire pallets, we just have a few dozen gallon jugs of different reagents.
A lab or a small shop setting.
Yeah. And the facility uses those specialized hazardous materials storage cabinets, the yellow ones. Since those cabinets are heavily engineered, fire-rated, and often ventilated, can we just consolidate our storage and put our strong acids and strong bases on different shelves inside the same specialized cabinet?
That is perhaps the single most common and most dangerous misconception in laboratory and small-scale industrial safety today.
Really?
The answer is absolutely not. The golden rule of chemical storage, which is basically written in blood across the industry, is that incompatible materials can never, under any circumstances, be stored within the same cabinet or the same exhausted enclosure.
Okay, I want to push back on that slightly just to understand the exact mechanism of failure here. If the cabinet has mechanical exhaust, like if it is actively sucking the air out of the interior and venting it safely outside, wouldn't that constant airflow immediately pull any fuming vapors away?
You would think so.
Right. It seems like an exhausted cabinet would be the safest place to put them because the dangerous gases are being constantly evacuated.
Let's visualize the actual airflow dynamics inside that cabinet, though. An exhaust system creates negative pressure. It pulls air from the room, through the vents in the cabinet doors, across the shelves, and up into the exhaust duct.
Okay, pulling bottom to top, usually.
Right. Now imagine you have an acid on the bottom shelf and an incompatible solvent on the top shelf, and both containers develop a slow leak.
So the vapors start to form.
And what happens to those vapors? Because the exhaust is pulling air continuously through the cabinet, the ventilation system itself acts as a mixing chamber.
Oh, no.
Yes. It draws the vapor from the acid on the bottom shelf directly upward, dragging it right across the leaking solvent on the top shelf before pulling them both into the ductwork together. You are artificially forcing the two incompatible vapors to collide in a highly confined, mechanically agitated space.
You've essentially built a carburetor for a bomb.
Exactly. Instead of safely evacuating the fumes, the airflow actually accelerates their interaction.
Oh.
And if a reaction occurs, it happens inside the confined space of the ductwork or the cabinet.
Which leads to an explosion.
A catastrophic overpressure event. Because a cabinet is designed to protect what is inside from a fire on the outside. It cannot protect the chemicals from each other.
Wow, that completely flips the intuition of ventilation on its head.
Yeah.
It really shows why separating these chemicals and managing their incompatibilities is the absolute first step. You cannot just engineer your way out of a chemical incompatibility by adding a fan.
You really can't. Separation is primary.
But, once we have our incompatible families living in completely different neighborhoods, we have to look at the sheer volume of liquids a facility uses just to operate on a daily basis.
A bulk storage.
Which brings us to the core hazard of flammable liquids and how we classify and limit them.
Right. The storage of flammable liquids is arguably the most heavily regulated aspect of physical safety on a work site, and for very good reason.
Let's start with the definition. Before we talk about how to store them, we have to establish what a flammable liquid actually is from a regulatory standpoint.
According to OSHA, a flammable liquid is defined as any liquid having a flash point of not more than 199.4 degrees Fahrenheit, which is 93 degrees Celsius.
Okay, let's break down that specific term, flash point. We hear it all the time on sites. But what is the actual thermodynamic reality of a flash point?
The flash point is the absolute minimum temperature at which a liquid gives off vapor within a test vessel in sufficient concentration to form an ignitable mixture with the air near the surface of the liquid.
So the critical distinction there is that the liquid itself is not actually what burns.
It never is. The liquid form of gasoline does not burn. The liquid form of acetone does not burn. What burns is the vapor.
That is such a crucial concept.
It is, because as a liquid sits in a container, the molecules are constantly vibrating. As the temperature rises, that kinetic energy increases. Eventually, the molecules at the surface of the liquid gain enough energy to break their intermolecular bonds and escape into the air above the liquid.
Vapor pressure.
Exactly, we call this vapor pressure.
It's almost like the liquid is sweating out this invisible, highly energized gas.
That is a highly accurate way to visualize it. And the flash point is simply the temperature at which the liquid is sweating so much of this vapor that if you were to introduce an ignition source like a static spark, an open flame, or even a hot surface, that vapor cloud hovering just above the liquid would instantly ignite.
And because different chemicals have completely different molecular structures, they require different amounts of heat to start shedding that vapor, which is where the globally harmonized system, or GHS, comes into play.
The GHS categories.
Right. It categorizes these liquids based on exactly how dangerous their flash points are.
And those categories are incredibly important for understanding risk on a site. Category 1 liquids are the absolute most dangerous. They have an extremely low flash point.
So they're off-gassing easily.
Very easily. This means a Category 1 liquid, like diethyl ether, is boiling off ignitable vapors at standard room temperatures, or even in freezing conditions. It is constantly producing a flammable atmosphere.
Whereas a Category 4 liquid would need to be physically heated up, maybe sitting next to an industrial furnace, or left out in the direct desert sun before it starts giving off enough vapor to actually be a hazard.
Exactly. The threshold is much higher.
But looking through the study materials for the ASP exam, the texts seem heavily focused on the middle ground. They spend an inordinate amount of time discussing Category 3 liquids.
They do, yes.
So why is Category 3 the primary focus, and what are the specific temperature parameters for it?
For the safety professional and the exam candidate, Category 3 is really the sweet spot of hazard, and that's because of how perfectly it aligns with real-world working conditions.
How so?
The specific definition you need to know is that a Category 3 flammable liquid has a flash point at or above 73 degrees Fahrenheit, but below 100 degrees Fahrenheit.
Okay, at or above 73 degrees and below 100 degrees. Let's think about that temperature band for a second. 73 degrees is standard room temperature in a normal climate-controlled building. And 100 degrees is just a typical summer afternoon in a warehouse without air conditioning.
You've hit the nail on the head. That's exactly it. A Category 3 liquid is so incredibly dangerous because it crosses the threshold into a highly volatile state based entirely on normal ambient fluctuations in the weather or the building's HVAC system.
So you don't even have to do anything to it.
Nothing at all. If you have a drum of a Category 3 solvent sitting in a receiving bay on a cool morning at, say, 65 degrees, it is relatively stable. It is below its flash point.
The vapor pressure is low.
But by 2 o'clock in the afternoon, the sun beats down on the metal roof, the ambient temperature in the bay hits 85 degrees, and suddenly, without anyone touching it or applying any external heat source, that drum begins off-gassing massive amounts of highly explosive vapor.
Wow. So the hazard state of the chemical changes dynamically based purely on the time of day. The environment itself becomes a trigger.
It creates a constantly shifting landscape of risk. And this leads us to a crucial escalation point in safety management. Because a typical facility might use hundreds of gallons of these Category 3 solvents or Category 2 fuels. But at what point does standard storage escalate into something entirely different?
When does a warehouse full of drums stop being just a storage facility and become a highly regulated, massively complex process safety management scenario under OSHA 1910.119?
Right.
Because this feels like the transition from managing a supply closet to operating a chemical refinery. OSHA must have a very specific metric that triggers this leap in oversight.
They do, and it is known throughout the industry as the 10,000-pound rule.
The 10,000-pound rule. Let's dig into that.
The PSM standard is officially triggered if a facility possesses a process involving a Category 1 flammable gas or a flammable liquid with a flash point below 100 degrees Fahrenheit, which encompasses Categories 1, 2, and those volatile Category 3 liquids we just discussed. Sure. If you have them on site in one location in a quantity of 10,000 pounds or more, you fall under PSM.
Let's talk about that metric, 10,000 pounds. First of all, why is the regulation based on weight instead of volume? I mean, we usually measure liquids in gallons. Why shift to pounds for this rule?
Because volume is variable, but mass is constant. The volume of a liquid actually expands and contracts based on temperature.
Oh, thermal expansion.
Exactly. If OSHA set the limit at, say, 1,500 gallons, a facility might have 400 and 490 gallons on a cold winter day, keeping them safely under the limit. But as the temperature rises in the summer and the liquid thermally expands, the physical volume might push past 1,500 gallons, accidentally triggering a massive PSM compliance violation.
Just because it got warm out.
Right. Furthermore, different chemicals have wildly different densities. 10,000 pounds of a highly dense solvent takes up far less physical space than 10,000 pounds of a light hydrocarbon.
So it standardizes the energy potential.
By focusing on weight, OSHA is focusing on the actual mass of the potential chemical energy present, regardless of how much space it takes up or how hot it is.
That makes a lot of sense. So 10,000 pounds is roughly 4,535 kilograms. To visualize that, a standard 55-gallon drum of a typical solvent might weigh around 400 pounds. So we were talking about roughly 25 drums in one location.
Give or take.
That is a substantial amount, but it is not an unimaginably massive facility. I mean, a medium-sized manufacturing plant could easily hit 25 drums of solvent.
Very easily. And the exact moment they cross that 10,000-pound threshold in a single connected process or a co-located area, their regulatory world changes overnight.
It's a whole new ballgame.
They are no longer just doing basic hazard communication and making sure they have enough fire extinguishers. They are now legally obligated to develop comprehensive process hazard analyses.
PHAs.
Yes. They have to implement strict management of change protocols for every single pipe and valve modification. They must have mechanical integrity programs involving non-destructive testing of their tanks.
This huge bureaucratic and engineering lift.
Massive. Because the assumption is that 10,000 pounds of volatile, flammable liquid represents a hazard so large that a failure wouldn't just cause a localized fire, it would result in a blast wave that could level the building and endanger the surrounding community.
But safety regulations always have caveats, right? And exemptions designed to reflect practical reality. Because I'm thinking a massive propane tank at a distribution center might easily hold more than 10,000 pounds of highly flammable gas. Does every single facility with a large heating tank fall under this massive PSM bureaucracy?
No, they don't. OSHA recognized that not all massive quantities of flammables represent the exact same level of complex risk. So there are two major exceptions to the 10,000-pound PSM rule that you absolutely must know for the exam.
Okay, what is the first one?
The first involves consumption. Hydrocarbon fuels used solely for workplace consumption as a fuel are exempt from the standard.
Solely for consumption as a fuel. Let's unpack the practical application of that.
Think about the massive propane bullet tank sitting outside a large Amazon-style fulfillment center. It is there to provide comfort heating for the million-square-foot building during the winter.
Or maybe a massive underground gasoline tank used exclusively to run a company's fleet of delivery trucks.
Perfect example. Those tanks easily hold tens of thousands of pounds of Category 1 flammable gas and Category 2 flammable liquids.
So why do they get a pass? A gas station holds a massive amount of potential energy, but we don't treat a local gas station like a chemical refinery.
Because the hazard, while severe, is completely static and universally understood. A propane tank powering a heater is a closed, simple system.
It just flows one way.
Right. The fuel moves from the tank through a pressure regulator and directly to a burner. It isn't being mixed with reactive chemicals. It isn't being subjected to complex heat exchange cycles or catalyzed reactions.
It's predictable.
Exactly. As long as those fuels are not part of another highly hazardous chemical process on site, they are exempt because the industry already possesses highly standardized, robust codes for simple fuel storage and dispensing.
So the complexity of the process dictates the severity of the regulation. That makes perfect sense. What is the second exemption to the 10,000-pound rule?
The second exemption applies to the physical state of the storage itself. Flammable liquids stored in atmospheric tanks are exempt, provided they are kept below their normal boiling point without the benefit of chilling or refrigeration.
Okay, we need to define an atmospheric tank. I assume it means the tank isn't pressurized.
Technically, an atmospheric tank is defined as operating at pressures from atmospheric pressure up through just 0.5 pounds per square inch gauge, or SIG. It is essentially unpressurized.
So if I have 20,000 pounds of a stable solvent sitting in a standard, unpressurized bulk storage tank, it is exempt from PSM.
Correct.
But why the caveat about chilling or refrigeration? Why does artificially cooling the liquid suddenly make it more dangerous and throw it back into the PSM requirements?
It goes back to our discussion on flash points and vapor pressure. If a chemical's natural boiling point at room temperature is so low that it would rapidly boil away into a massive explosive cloud, the only way to store it as a liquid is to continuously refrigerate it.
Okay, so it has to be kept cold just to exist as a liquid.
Right. The exemption goes away because you are now relying on an active mechanical system, a refrigeration compressor, electrical power, coolant lines to keep the hazard at bay.
The hazard is no longer static.
Exactly. If the power goes out or the compressor fails, that liquid is going to rapidly heat up, boil, overpressurize the tank, and cause a catastrophic failure.
It's a ticking clock if the power drops.
The system relies on active mechanical intervention to remain safe. Therefore, the risk is much higher, the complexity is higher, and OSHA requires the full weight of the process safety management standard to ensure those active systems do not fail.
But an atmospheric tank holding a stable liquid, however, is just a steel bucket with a lid. It is passive safety.
Completely passive.
That distinction between active mechanical safety and passive static safety is a massive insight. It completely changes how you look at the equipment on a site. But let's bring this back to the everyday reality of a typical facility.
Yeah.
Let's say a site doesn't hit the 10,000-pound PSM threshold. They have maybe 500 gallons of various flammable liquids. They're exempt from the refinery-level oversight, but they still have to physically store these liquids safely.
They do.
They can't just leave drums sitting next to the break room or stacked randomly in the aisles.
Definitely not. And this brings us into the realm of architectural safety. We have to construct dedicated environments for these hazards.
Inside storage rooms.
Well, let's start with the baseline limits before a facility even builds a specialized room. If you are just walking through a general manufacturing area, OSHA states that no more than 25 gallons of flammable or combustible liquids can be stored outside of an approved storage cabinet.
25 gallons. Wait, a standard industrial drum is 55 gallons. So you can't even have half a drum of solvent just sitting freely on the shop floor without putting in specialized containment.
That's right. The intention is to strictly limit the available fuel load in an open working environment. If a fire starts at a workstation, 25 gallons is a manageable amount of secondary fuel for the sprinkler system and local responders to handle.
It won't overwhelm the system.
Exactly. Anything more than that introduces a cascading failure risk. So if you have funnel gallons, it must go into an approved flammable storage cabinet. And even those cabinets have internal limits to prevent them from becoming concentrated bombs.
Okay, what are the capacity limits for a single cabinet?
A single approved cabinet can hold no more than 60 gallons of a flammable liquid or 120 gallons of a combustible liquid.
Okay, let's explore that discrepancy. You are allowed to store double the amount of combustible liquid compared to flammable liquid in the exact same physical space. Is that purely tied to the flashpoint temperatures we discussed earlier?
It is entirely tied to the flashpoint. Combustible liquids have higher flash points, generally starting at 100 degrees Fahrenheit and going up. They require much more thermal energy to produce an ignitable vapor cloud.
They are just harder to set on fire.
Right. Because they are inherently more stable at room temperature, the regulations grant you the flexibility to store a larger volume of them in a single cabinet.
While flammable liquids are volatile and eager to ignite.
Very eager. Therefore, the maximum allowable concentration is restricted to 60 gallons to limit the potential explosive yield if the cabinet were to fail in a fire. And of course, every one of these cabinets must be conspicuously labeled with the iconic warning, "Flammable, keep fire away."
It seems straightforward enough, but 60 gallons per cabinet is a drop in the bucket for a facility doing large-scale painting, coating, or chemical mixing.
Oh, absolutely. They burn through that in hours.
Right. They're going to need more than a few yellow metal cabinets. They're going to need to dedicate actual architectural space to the hazard. I want to spend some time visualizing walking into one of these dedicated spaces, an inside storage room.
Let's do it.
In my mind, based on the severity of these chemicals, it feels like stepping into a bank vault. Heavy concrete, sterile, imposing. What are the specific physical and geometric dimensions that OSHA actually demands when you construct one of these rooms?
The regulations are remarkably granular because, as you noted in your opening scenario, this room is essentially a containment vessel for a potential disaster. Every inch of its geometry is calculated to either prevent an incident or mitigate the fallout of a fire.
Okay, where do we start?
Let's start with the floor plan and how human beings interact with the space. There must be one clear aisle at least 36 inches wide.
36 inches. That is exactly 3 feet. It is the standard width of a commercial doorway. But why is the aisle width codified in a chemical storage regulation? Is that for the workers to load the drums, or is it for emergency response?
It serves a dual critical purpose under extreme duress. First, consider the evacuation scenario. If a flash fire occurs in that room, the worker inside has mere seconds to escape before the thermal radiation and toxic smoke become lethal.
They just have to run.
They cannot be navigating a maze of pallets or tripping over 5-gallon pails. The 36-inch aisle provides a guaranteed, unobstructed, straight-line path to the exit.
A clear shot out. And the second purpose.
Second, consider the offensive firefighting scenario. When a specialized hazardous materials response team or a fire crew enters that room, they are wearing heavy bunker gear, carrying self-contained breathing apparatus on their backs, and dragging a charged, pressurized fire hose.
That adds a lot of bulk.
That gear drastically increases the physical width of a human being. If the aisle is only 24 inches wide, the firefighters will physically wedge themselves between the burning drums. They won't be able to advance the hose.
So a 36-inch aisle is the minimum calculated width to allow a fully encumbered firefighter to advance into the space, maneuver their equipment, and aggressively attack the fire at its source.
Exactly. The architecture is built around the dimensions of a worst-case scenario.
That makes total sense for the floor plan. What about the vertical space? Because in modern logistics, the entire goal is to build vertically. You see warehouses with automated racks stacked 40 feet to the ceiling. Can we maximize the footprint of our inside storage room by stacking the drums?
OSHA has a very hard rule against this to prevent structural cascade failures. Containers over 30 gallons in capacity cannot be stacked one upon the other in these rooms.
Let's investigate the physics of that. A standard 55-gallon steel drum is an incredibly robust piece of engineering. I mean, you can hit it with a forklift and it usually just dents. Why can't I place one heavy steel drum on top of another?
Well, under normal ambient conditions, you absolutely can. The steel can bear the weight easily, but safety regulations are not written for normal conditions. They are written for the moment the room catches fire.
Okay.
Let's look at the thermal mechanics. When a fire breaks out, the ambient temperature in the room skyrockets. The steel drums begin to absorb that thermal energy. Two things happen simultaneously.
What's the first?
First, the flammable liquid inside the drum begins to boil, rapidly expanding and creating massive internal pressure. Second, as the steel of the drum heats up, it loses its structural tensile strength. The metal softens and weakens.
So the container is simultaneously becoming weaker on the outside while being pressurized like a bomb on the inside.
Exactly. Now imagine a second 55-gallon drum weighing 400 pounds sitting on top of that weakening bottom drum.
Oh, I see where this is going.
As the heat compromises the structural integrity of the bottom drum, it can no longer support the 400 pounds bearing down on its lid. The bottom drum crushes inward, the internal pressure violently breaches the seams, and 55 gallons of boiling flammable liquid instantly dumps directly into the fire,
Creating a massive thermal plume that will likely breach the room itself.
Yes. By forbidding the stacking of large containers, OSHA eliminates the crushing weight that accelerates the failure of the container during a thermal event.
It is about buying time. The unstacked drum will eventually fail in a fire, but it will take much longer without 400 pounds trying to crush it while it burns.
Buying time is the essence of fire safety.
Okay, so we have clear aisles and unstacked drums. Let's talk about the boundary of the room itself, the door. I imagine a heavy, fire-rated vault door.
It absolutely must be a fire-rated door tested to withstand intense heat for a specified duration without warping or failing. But the most critical mechanical feature of the door isn't its thickness, it is its behavior. The room requires self-closing fire doors.
Because in a panic, a human being cannot be trusted to perform a safety function.
Exactly. Human psychology during a crisis dictates that the primary objective is flight. If a worker drops a drum and it ignites, their sympathetic nervous system takes over. They are going to sprint through that doorway to save their own life.
They're not going to pause, turn around, grab the handle, and gently pull the door shut to contain the fire.
Never. If the door isn't mechanically engineered to close itself via a hydraulic arm or a fusible link that melts and releases a heavy spring, the door stays wide open. The fire, seeking oxygen, will instantly roll out of the room, travel down the hallway, and consume the entire manufacturing facility.
The self-closing mechanism completely removes human error from the containment strategy. The room just seals itself.
It has to.
And this leads us to the internal systems of the room, specifically electricity.
Yeah.
You walk into this sealed, windowless room, and it's pitch black. You reach for the light switch on the wall. In a normal house, when you flip a light switch, there is a tiny physical disconnection of a metal contact behind the plastic plate, which creates a microscopic electrical arc.
A tiny spark.
A spark that happens every single time you turn on a light in your living room. Now, if you introduce that tiny spark into an inside storage room that happens to be filled with the heavy vapors of a Category 1 flammable liquid, flipping that switch is the detonator.
It absolutely is.
You are dead. So how does the code solve the problem of electricity in a vapor-rich environment?
This is where we get into highly specialized electrical engineering. The standard requires that all electrical wiring and equipment inside that room must be approved for Class 1, Division 1 hazardous locations.
Let's decode that classification. What does Class I mean, and what does Division 1 mean?
The National Electrical Code breaks down hazards into classes and divisions. Class I simply means that flammable gases, or vapors produced by flammable liquids, are present in the air in quantities sufficient to produce explosive or ignitable mixtures.
So we aren't dealing with combustible dust or flying fibers.
No, we are dealing with explosive gas. That is Class 1.
And Division 1?
Division 1 refers to the probability of that gas being present. Division 1 means that the hazardous, explosive concentrations of gas exist continuously, intermittently, or periodically under normal, everyday operating conditions.
It isn't a rare accident. The danger is assumed to be present just by the room doing its job.
Yes.
So a Class 1, Division 1 environment is the most dangerous possible scenario. It is a room full of explosive gas all the time.
Yeah.
How do you design a light switch or a lighting fixture to operate safely in that environment?
How would you do it?
Well, my assumption would be that you create a completely hermetic seal. You build a thick plastic box around the switch, you pump it full of silicone, and you make absolutely sure that no vapor from the room can ever penetrate the box and reach the spark.
That is the intuitive assumption, but it is actually mechanically impossible over the long term.
Really? You can't seal it?
You cannot build. It assumes that when you flip the switch, The internal spark will ignite the gas inside the metal housing, causing a tiny internal explosion.
Wait, it allows an explosion to happen inside the light switch on the wall.
Yes, it expects it. But the engineering marvel is how the enclosure manages that internal explosion. The metal housing is cast from incredibly thick, heavy aluminum or iron. It is designed to easily withstand the massive internal pressure of the gas detonating.
Okay, so it contains the blast.
But more importantly, the casing must vent the expanding, burning gases from that internal explosion back out into the room so the casing doesn't just shatter like a grenade.
But if it vents burning superheated gas out into a room full of flammable vapor, won't that just ignite the whole room anyway?
Not if you cool the gas first. And this is the magic of the design. The joints of a Class I Div 1 enclosure are heavily threaded sometimes with 5 or 6 full threads of engagement, or they have wide, precision-machined flat flanges.
Okay, like a maze of metal.
Exactly. When the internal explosion happens, the superheated, expanding gases are forced to travel through the microscopic labyrinth of those metal threads, or across that long, flat flange before they can escape into the room.
And what does that do?
As the hot gas squeezes through that tight metal pathway, the massive metal casing acts as a heat sink. It physically absorbs the thermal energy from the gas. By the time the gas finally escapes the switch housing and enters the room, it has been cooled below the ignition temperature of the surrounding vapors.
That is absolutely phenomenal engineering. The fixture doesn't prevent the explosion, it contains the pressure, and uses a mechanical heat sink to quench the flame front before it can escape. It literally swallows the hazard.
It's passive engineering at its absolute finest. But you were touching on a critical flaw if we just stop the design there.
How so?
Well, you have a sealed room with self-closing doors, unstacked drums, and brilliant explosion-proof electrical fixtures. You have contained all the ignition sources. But if you just lock those chemicals in a tight, fire-rated concrete box, those liquids are continuously off-gassing.
Oh, right. The vapors.
The vapors are going to build and build and build.
The vapor pressure in the room will continually rise until it is just a hyper-concentrated fuel air explosive.
Which is why the room cannot remain perfectly sealed from a fluid dynamic standpoint. You have to let the room breathe. And that brings us to the invisible control. Ventilation engineering.
In the hierarchy of controls, where you try to eliminate the hazard, substitute it, engineer it out, use administrative controls, or default to PPE ventilation, sits squarely in the middle as a primary engineering control.
We can't eliminate the chemicals because the factory needs them to operate. We can't substitute them. So we must mechanically engineer the atmosphere of the room to strip the hazard out of the air.
So how much breathing does OSHA require this room to do?
The exam candidate needs to memorize this specific metric. OSHA requires 6 complete air changes per hour for a flammable liquid storage room.
6. Let's do the math on that. 6 complete air changes per hour means that every 10 minutes, the entire volumetric capacity of the air in that room, floor to ceiling, corner to corner, must be completely evacuated and replaced with fresh, uncontaminated air.
It is a massive amount of fluid movement. It creates a constant, aggressive dilution of any volatile vapors that might be off-gassing from microscopic leaks, bung caps, or residual spills.
It functions exactly like a set of mechanical lungs. The room requires this constant measured rhythm of inhaling fresh air from the outside and forcefully exhaling the dangerous vapors. But how exactly do we design this respiratory system?
The placement is key.
Because I was reading the design specs, and it stated that the exhaust system, whether it relies on gravity or mechanical fans, must commence not more than 12 inches above the floor. Why so incredibly low? When I think of an exhaust fan, I think of my bathroom ceiling. You put the fan at the highest point to suck the air up and out.
Right, but the bathroom fan works because hot steam from a shower is lighter than ambient air. It rises via thermal convection. But chemical vapors do not behave like steam at all.
They don't rise.
No. The vast majority of hazardous, flammable chemical vapors like gasoline fumes, acetone, or toluene have a vapor density that is significantly heavier than ambient air.
They are physically heavier than the air around them.
Yes. They do not rise. When they off-gas from a drum, they sink. They fall to the floor like an invisible waterfall, and they just pool there. They spread out across the concrete like an invisible layer of molasses.
Wow, okay.
If an engineer were to install the exhaust fan in the ceiling of the storage room, the fan would pull massive amounts of fresh air through the door vents and immediately exhaust it out the roof. The room would technically achieve 6 air changes per hour, but the heavy, dangerous layer of explosive vapor sitting on the floor would remain completely undisturbed.
Fresh air would just breeze right over the top of it.
Exactly. By legally mandating that the exhaust duct commences within 12 inches of the floor, the ventilation system is forced to actively sweep and vacuum that heavy, stagnant layer of danger directly off the concrete.
It is like draining a pool from the main drain at the bottom, rather than trying to skim water off the top. You are targeting the heaviest concentration of the hazard.
It's the only way to effectively clear the room.
And how do we control this mechanical breathing? We talked about the brilliance of the Class I Div 1 switches inside the room earlier. Do we use an explosion-proof switch inside to turn on the fan?
You could, technically, but the code relies on behavioral engineering here. For a mechanical ventilation system, the control switch must be located entirely outside the door.
Why outside?
Because you never want a worker to enter a potentially explosive, stagnant atmosphere and then try to turn on the safety systems. The switch must be engaged from the safety of the exterior hallway. You turn the lungs on, you wait a moment for the air to clear, and then you enter.
That makes perfect sense.
Furthermore, that switch must be wired to operate both the ventilation equipment and the lighting fixtures simultaneously.
That is a phenomenal failsafe. You cannot physically turn on the lights to see what you are doing without also activating the exhaust fans. The safety mechanism is inextricably linked to the operational requirement.
Exactly. You can't bypass it. And the code adds one more layer of visual communication. If liquids are actually being actively dispensed inside the room, meaning workers are opening the drums, breaking the seals, and pouring volatile liquids from one container to another, which drastically increases vapor release, there must be an electric pilot light located adjacent to the switch outside the door.
A warning light.
It serves as a visual indicator to anyone walking by that the room is in active high-hazard use, and it confirms that the ventilation system is powered and running.
So, we are moving all this air, we are exhausting from the floor, we have fail-safes on the switches. But what is the ultimate mathematical goal of this airflow? We know we want the vapors gone, but is there a specific target concentration that the engineers are trying to hit with these calculations?
The overarching thermodynamic goal of the ventilation system is to maintain the concentration of flammable vapor in the room at or below 10% of the lower flammable limit, or LFL.
The lower flammable limit, we need to dissect that term for a second. The LFL is the absolute minimum concentration of vapor in the air that is mathematically required to sustain combustion.
To visualize LFL, think about trying to start a campfire. If you just have a massive pile of logs and you drop a single match on it, nothing happens. You need the right mixture of fuel and oxygen.
Right.
In a vapor cloud, it is called stoichiometry. If you have a room full of air and just a tiny microscopic trace of gasoline vapor, a spark will do nothing. The mixture is too lean, the fuel molecules are too far apart to chain react.
They can't jump to each other.
Exactly. The LFL is the precise percentage of vapor in the air, where the fuel molecules are finally close enough together that a spark will jump from one to the next, propagating a flame front.
So if a chemical has an LFL of, say, 2% by volume in the air, the moment the vapor concentration hits 2%, the room is primed to explode. And the OSHA rule says we have to design the ventilation to keep the concentration at or below 10% of that minimum threshold.
Right. We want to stay 10 times below the absolute minimum danger zone. It provides a massive 90% margin of error to account for sudden spills, ventilation fan degradation, or particularly hot days where vapor pressure spikes.
That's a huge buffer.
And for engineers designing these systems in larger industrial plants using Class I liquids, OSHA removes the guesswork entirely. The regulation dictates a specific flow rate rule. Mechanical ventilation must operate at a rate of no less than 1 cubic foot per minute of exhaust per square foot of solid floor area.
That makes the math incredibly simple. If a facility constructs a 500 square foot chemical vault, the engineer simply specifies an exhaust fan capable of pulling 500 cubic feet per minute.
It creates a standardized, foolproof baseline for the engineering control.
Okay, all of these architectural and ventilation rules are incredibly robust for a static environment. They are perfect for when the chemicals are just sitting still, locked in a dark room, behaving themselves.
But factories aren't static.
Exactly. The reality of manufacturing is kinetic. Work sites are active. We have to take these materials out of the vault. We have to move them across the factory floor. We have to pump them through hoses, pour them into vats, and sometimes store the overflow in the great outdoors. This brings us to the physical interaction with the hazard. Clearances, transfers, and the physics of movement.
The physical environment surrounding the storage is just as vital as the room itself. Let's start with how we arrange the space inside the facility. Clearances are strictly, aggressively regulated.
What's the first one?
For example, you must maintain a physical clearance of at least 36 inches between the top level of stored material and the sprinkler deflectors on the ceiling.
A 3-foot gap of empty air between the top of the pallets and the fire sprinklers. It seems like wasted vertical space in a tight warehouse. Why is that gap so critical?
We have to look at the fluid dynamics of how a fire sprinkler actually operates. A sprinkler head doesn't just drop water straight down like a faucet. When the heat-sensitive bulb shatters, pressurized water hits the metallic deflector plate and is sheared outward in a wide umbrella-shaped pattern.
Covering a wide area.
Yes. This pattern is engineered to cover a specific square footage of the floor. If a warehouse manager stacks cardboard boxes of combustible materials right up to within 6 inches of the sprinkler head, the physical mass of the boxes will completely block the umbrella pattern from forming.
The boxes become an umbrella against the water.
Exactly. If a fire starts underneath or behind that high stack, the fire will rage on, completely shielded from the sprinkler suppression water. The water will just bounce off the top box while the fire consumes the rack below. The mandatory 36-inch clearance provides the necessary unobstructed physical space for the pressurized water spray to fully develop its pattern and drive downward into the fire plume.
That makes incredible sense. It is about protecting the suppression mechanism itself. What about horizontal clearances? We talked about fire doors earlier.
You must maintain 24 inches of clear space around the entire arc of travel of a fire door unless there is a physical barricade installed to prevent storage. Furthermore, you cannot store any material whatsoever within 36 inches of a fire door opening.
Because if a fire breaks out, that self-closing door we talked about needs to swing shut unimpeded. If someone absent-mindedly leaves a pallet jack or a stack of pails right next to the door swings, hits the obstruction, and stops.
The vault remains open, the fire spreads.
It defeats millions of dollars of safety engineering with a single misplaced box.
It really does. You must also ruthlessly maintain clearances around exits and stairways. It sounds like basic common sense, but in a busy facility running out of floor space, the temptation to tuck a pallet of materials into a stairwell landing is immense.
I've seen it happen.
But in an emergency, that stairwell is the only evacuation route for the workers on the second floor and the primary attack route for the fire department. It has to stay clear.
Okay, so we've mapped out the clearances. Now let's tackle the movement. Transferring liquids. To me, transferring a volatile solvent from a bulk drum into a smaller usage container seems like the moment of absolute highest vulnerability.
It is the most dangerous routine task.
The liquid is out of the drum. It is actively exposed to the open air. Splashing generates massive amounts of vapor, and it's moving through a mechanical pump or a hose. Besides ensuring you have ventilation and physical distance from other operations, which I believe the code specifies as a 25-foot separation or a 1-hour fire-rated barrier for transferring more than 5 gallons. What is the hidden danger here? What is stopping a static spark from igniting that massive vapor cloud?
You are honing in on one of the most insidious hazards in fluid dynamics. The danger of static electricity during liquid transfer cannot be overstated. We have to dive into the physics of triboelectric charging.
Triboelectric charging. Break that down for us.
When a non-conductive, flammable liquid, like a hydrocarbon solvent or a fuel, flows rapidly through a pipe or a rubber hose, it creates friction against the interior walls of that hose. This physical friction physically strips electrons from the molecules of the liquid or the hose.
So the liquid essentially becomes electrically charged as it moves.
Yes. It is the exact same mechanical process as walking across a dry carpet in your socks and then touching a metal doorknob. The friction of your socks on the carpet builds up a static electrical charge on your body, and the spark jumps to the metal to release the energy.
It is the exact same physics, but scaled up to a lethal industrial level.
Exactly. The liquid flowing through the hose builds up a massive static charge. As the liquid pours into the receiving metal drum, it transfers that electrical charge to the drum. If that receiving drum is sitting on a wooden pallet or a rubber mat, which are insulators, the electrical charge has nowhere to go.
It just sits
Yeah,
there.
it just builds and builds and builds on the skin of the metal drum.
Until it seeks a path of less resistance.
Right. And nature always seeks equilibrium. Eventually, the voltage potential becomes so high that the electrical charge will violently tear through the resistance of the air itself, jumping from the charged drum to the nearest grounded object, which might be the metal nozzle of the hose you're holding.
And the space between the nozzle and the drum is exactly where the flammable liquid is splashing and creating a massive concentrated vapor cloud. A microscopic spark jumps through a cloud of fuel that is above its LFL. Boom. You have a catastrophic deflagration in the worker's hands. So how do we engineer a defense against static electricity?
The code demands two interconnected techniques, bonding and grounding. They sound similar, but they perform two distinct electrical functions. Bonding means physically connecting a conductive wire between the dispensing container and the receiving container.
You literally clip a metal wire with alligator clips from the big drum to the little drum.
Yes. Bonding equalizes the electrical potential between the two objects. If both drums are connected by a wire, the static charge flows freely between them, keeping them at the exact same electrical voltage. Because there is no difference in voltage between the two drums, a spark cannot jump between them.
But both drums are now highly charged. They're equal, but they're both holding the static energy.
Which is why bonding alone is insufficient. You must also implement grounding. Grounding means connecting a conductive wire from one of those bonded containers directly to the earth.
The literal earth.
Yes. This is usually done by clipping a wire to a dedicated copper ground rod driven deep into the soil, or attaching it to the structural steel framework of the building, which is inherently tied to the earth.
So grounding creates an invisible, infinitely wide electrical highway. As the fluid friction generates the static electrons, the bonding wire shares the electrons between the drums, and the grounding wire immediately drains all of those electrons safely away into the massive heat sink of the Earth. The charge never builds up. The spark never happens.
It safely bleeds off the kinetic energy of the fluid transfer. It is a brilliant, entirely passive safety system, provided the workers have the operational discipline to attach the clips every single time.
That human element again.
Always. And speaking of operational discipline, while we are talking about active work sites, we absolutely cannot ignore the most fundamental administrative control: housekeeping.
Housekeeping always sounds like a euphemism for, sweeping the floor. It sounds like an HR directive, not a critical safety protocol.
That is a dangerous underestimation. In hazardous materials management, housekeeping is a life-or-death engineering control. We aren't just talking about keeping the aisles clear of trip hazards. The code specifically mandates providing designated containers with tight-fitting covers for the collection and separation of oily used rags and hazardous waste.
Why are oily rags singled out in the fire code? I mean, they're just rags used to wipe down machinery.
Because they introduce the terrifying phenomenon of spontaneous combustion. Let's look at the chemistry of a rag soaked in linseed oil or a standard industrial machine oil. When the oil is exposed to the oxygen in the ambient air, it undergoes a slow oxidation process.
Okay, oxidation.
Oxidation is an exothermic reaction. It inherently generates thermal energy.
Like rusting metal, but faster.
Exactly. Now, if a worker uses an oily rag and lays it out flat on a concrete floor, the oil oxidizes, generates a tiny amount of heat, and that heat is immediately dissipated into the cool air of the room. It is relatively harmless.
But if they throw it in a pile?
Yes. If a worker takes 50 oily rags and tosses them into a massive concentrated pile in the corner of a warm warehouse, the physics change entirely.
The pile itself becomes an insulator.
The rags in the center of the pile are oxidizing and generating heat. But because they are buried under layers of other rags, the heat cannot escape into the air. The temperature in the center of the pile begins to rise.
Oh, this is bad.
As the temperature rises, the rate of oxidation accelerates, which generates even more heat. It becomes a runaway thermal feedback loop. Eventually, the temperature in the center of that rag pile reaches the auto-ignition temperature of the cotton or the oil. Without a spark, without a flame, without any human intervention, the pile simply bursts into a raging fire.
The hazard literally generates its own ignition source. That is terrifying. So how does the code mitigate this?
By mandating small, self-closing metal waste containers. First, the small size physically limits the accumulated mass of the rags, preventing a massive thermal core from forming.
You just can't fit enough in there to reach critical mass.
Exactly. Second, the metal container conducts heat, helping to dissipate the internal thermal energy outward into the room. And finally, the self-closing, tight-fitting lid starves the environment of oxygen. If the rags do start to heat up and smoke, they quickly consume the small amount of oxygen inside the sealed can, and the reaction smothers itself before a fire can break out.
The details of these regulations really are written in the ashes of past disasters. Every rule is a countermeasure to a specific physical law.
They absolutely are.
Finally, let's briefly touch on storing these materials outside. If a facility runs out of space inside the vault, they might move combustible pallets out into the yard. What are the rules for the great outdoors?
The environment changes, but the core principles of segregation and geometry remain. For outdoor storage, the rules dictate that combustible materials stored outdoors must not be placed within 10 feet of a building or structure.
10 feet provides a thermal break. If the pallet catches fire in the yard, the radiant heat and direct flame impingement won't immediately compromise the siding of the factory and spread the fire indoors.
Exactly. Furthermore, the code states that outdoor piles of combustible materials cannot exceed 20 feet in height.
Why cap the height at 20 feet? Is that a structural stability issue for the pallets?
Stability is part of it, to prevent a collapse that could injure a worker. But the primary driver is firefighting logistics. Standard municipal fire department hose streams and aerial apparatus are highly effective at penetrating and suppressing fires up to about 20 feet in height from the ground.
But above that,
if a pile is 40 feet tall, the water stream cannot penetrate the thermal column to reach the seat of the fire at the top. The fire will simply rage out of control at the crown of the pile. Keeping the pile under 20 feet ensures that emergency responders always have a tactical advantage.
it is incredible how these highly specific, seemingly random numbers, 20 feet of separation for incompatibles, 18-inch partition extensions, 36-inch clearances for sprinklers, 10-foot boundaries for outdoor piles, they all form this incredibly cohesive, interlocked architecture of safety.
They do. They all work together.
When you study them individually for an exam, they can feel like arbitrary bureaucratic hurdles. But when you unpack the fluid dynamics of a vapor cloud, the thermal degradation of a steel drum, or the static generation in a hose, you see the invisible physics that the codes are actively fighting against.
And that is the exact paradigm shift that an ASP candidate or a seasoned safety professional must undergo. You are not a compliance officer checking boxes on a clipboard. You are a physical engineer managing volatile potential energy. The regulations are simply your tools.
Let's summarize the immense ground we've covered today. Our mission was mastering the mechanics of segregation and separation. We decoded the chemistry of incompatible materials, understanding why they demand 20 feet of physical distance to allow for vapor dilution and spill response.
Or an isolation partition that extends 18 inches beyond the materials to physically catch pressurized splashes and block creeping vapors.
We analyzed the thermodynamics of flashpoints and how Category 3 liquids become highly volatile simply based on summer weather. We explored the massive 10,000-pound PSM threshold and why complex active chemical processes require refinery-level oversight while passive atmospheric tanks and consumption fuels are exempt.
We mentally constructed an inside storage room examining the necessity of 3-foot aisles for emergency egress, the prohibition on stacking drums to prevent thermal crushing in a fire, and the brilliant passive heat sink engineering of Class I Division I explosion-proof electrical fixtures.
We made the invisible fluid dynamics of ventilation visible, detailing why a room requires 6 complete air changes per hour, why the exhaust ducts must pull from within 12 inches of the floor to capture heavy vapors, and why the goal is always to maintain the atmosphere safely below 10% of the lower flammable limit.
And we finished by exploring the kinetic dangers of movement, understanding how friction strips electrons to create static sparks, how bonding and grounding equalize and drain that electrical potential, and how the exothermic oxidation of oily rags requires sealed metal cans to prevent spontaneous combustion.
This session of QHSE Talks has armed you, the listener, with the exact mechanical understanding needed not just to excel on an exam, but to walk onto a site and see the invisible hazards that everyone else is missing.
But I want to leave you with a final, slightly provocative thought to reflect on.
Okay, let's hear it.
Throughout this entire discussion, we have relied heavily on static engineering controls. We design the perfect 36-inch clearance. We calculate the flawless 6 air changes per hour. We install the heavy explosion-proof switches. We build the perfect room, and we assume the facility is safe. But what happens when the operational reality of business evolves?
Well, factories are incredibly dynamic ecosystems. They change every day.
Precisely. What happens when purchasing decides to save money by switching from a stable Category 4 solvent to a highly volatile Category 1 solvent, and suddenly your existing ventilation calculations are entirely insufficient for the new vapor load?
Oh, wow.
Or what happens when a building gets repurposed and a contractor installs a new interior partition wall that inadvertently blocks the airflow to your floor-level exhaust duct? The true test of a safety professional is not your ability to memorize these rules on day one of a new build.
It is the vigilance to maintain them.
It is operational discipline. It is the ability to look at a bustling, chaotic worksite and recognize when a subtle operational change, a new chemical, a relocated rack, a blocked aisle, has secretly invalidated your entire framework of separation and ventilation controls. You have to constantly reevaluate the physics of your environment.
That is a sobering but vital reality check. The environment is always changing, and those invisible lines of safety can be erased without anyone noticing if you aren't actively paying attention. The X-ray machine of safety is always moving, and you have to keep interpreting the image. Thank you for joining us at the table for this session of QHSE Talks. Understanding these complex physical mechanics makes you more than just an employee. It makes you the architect and the guardian of the worksite. Stay vigilant, keep asking why, and we'll catch you on the next one.